nice and like very good barbecue atmosphere. So there is one place where the pastor who runs the barbecue.
Yeah, church's barbecue.
Yeah.
Yeah, I went there once or twice because I've read about it. Yeah, it's okay. It's okay.
I think the sausage was better than.
So what you went there when?
I think 1 year back.
Yeah.
Yeah.
Did you just went just for the experience? Then?
I mean, I'm coming back from with some friends coming back from Houston, so we said let's go through that.
Yeah, I think it has been featured on some of the food channel.
Yeah.
Right. Okay. So, pleasure to have Kenny here. Can you pronounce your last name for me?
It's
Okay. Okay, so Kenny's a graduate student at Ohio State, finishing up his PhD this year, working with John Beacom and Anna Peter. And he overlapped with Sheldon when he was there, and everybody knows Sheldon, of course. So, okay, so today he's going to talk about searching for sterile neutrino dark matter with X-rays and velocity spectroscopy.
Thanks. And thanks for having me here. It's a very nice campus, and I enjoy talking to people during the lunch. It's a very active discussion. I will be here till Friday, so I will have more of that. So today we're going to talk about sterile neutrino dark matter and some of the recent developments and also new ideas that we have. So let's talk about dark matter. So by now we have so many overwhelming evidence that the universe needs a dark matter. So this is one of the strongest evidence that I personally think of. From the angular distribution of the CMB, we know that we need a significant component of non-baryonic matter, so that stuff that acts like a matter in the universe, about 23% of that. And it has to be non-baryonic because it cannot couple strongly with photon. And then another very strong evidence that we have for the evidence of dark matter is this picture, bullet cluster. So what's happening here is two clusters, they have collided with each other. So galaxies, they just pass through each other and experience any collisions or interactions. And here in red are the X-ray, the hot gas. So hot gas actually acts strongly against each other through standard model, standard interactions. And we use X-ray, we can map out gas. But what we find is most of the mass seen from gravitational lensing actually is contains these two regions. That means there's a significant mass component that just pass through each other, meaning they don't act on each other very strongly. So that's very different from the baryonic gas in the red. So this picture, I think, proves that what we see from CMB is really some new matter. It's not just a sonic trick. The gravity acts differently in large scales. So we have this picture of living dark matter. And dark matter works very well in large scales like CMB and galaxy clusters. But recently, people have been finding maybe there's some problems for this cold dark matter picture in small scales. So what's shown here is, if you look at the density distribution of dark matter, gravitational matter within dark matter halos. So what people normally characterize the dark matter halo is density slope towards in the small radius. If you look at the kinematics of the galaxies, and it turns out you find out galaxies, actual galaxies, prefer a much shallower slope than what's been found in simulations. So this is so-called the core and cusp problem. And by the way, so for simulation, it's only dark matter only simulation. So this is so-called the core and cusp problem, one of the small-scale dark matter anomalies. Another anomaly people found is, people claim that there is, it's called the missing satellite problem. Again, if you look at dark matter only simulations, you found a lot of dark matter halos, so circled here. And then you count these halos, you compare to observations of Milky Way satellites, galaxies, you can identify them, right? And then once you exhaust all the Milky Way satellite galaxies, then you ask, where are the other subhalos found in your simulation? Why they do not show up in observations? So this is so-called missing satellite problem. Another slightly different problem, but probably closely related, is so-called the too big to fail problem. So again, from cold dark matter simulations, you pick all your dark matter subhalos in your simulation, and you plot their velocity, circular velocity versus radius. Okay, so each line here corresponds to one subhalos from a simulation. And you say, okay, Milky Way satellites, they must be matched into one of these lines, so you can plot Milky Way satellite observations. So each one of the points here corresponds to one Milky Way satellite galaxies. So what people have found is that there are a significant number of subhalos in the dark matter only simulations that does not match the observation. Okay. So, and these guys all have higher peak velocity than what's been seen in the Milky Way satellite galaxies. So they are more massive objects. And then you ask, why is these more massive subhalos does not host a galaxy, also optical galaxy? So people call this too big to fail problem. So if this problem is statistically significant, that means there's only two possible outcomes. It's that one, either our simulation, dark matter only simulation, is wrong, meaning that it cannot match the theory behind these galaxy formations. Or maybe our hypothesis of dark matter is wrong. In particular here, our hypothesis is cold dark matter. So let's recap. Obviously, we need dark matter, okay? But from small scale problems, there's probably hints that dark matter may not simply be cold. Of course, we always have the trivial, we always have the problem of we don't know how to take into account baryons during simulation. But if dark matter is not a cold dark matter, it can be self-interacting. So self-interacting can transfer energy in dense areas of the dark matter halo, and then we can solve some of the small scale problems. Dark matter can also be decaying dark matter. We can get momentum keg during some time in the early universe, or late time, depends your sense of early and late. That can also help solve the small scale problems. Or it can be warm, meaning that it has a non-trivial velocity distribution when structure formation happens. Okay. So today I'm going to talk about one of the dark matter candidates that's been studied a lot. It's called Sterile Neutrino Dark Matter. And it's related to these because Sterile Neutrino Dark Matter can be a warm dark matter candidate. Okay. So when people talk about dark matter, we first need to ask, how is dark matter being produced? Sterile Neutrino Dark Matter is not a typical WIM dark matter candidate. It's not produced by thermal collisions and thermal freeze-outs during early universe. So one of the very early proposals of Sterile Neutrino Dark Matter is we can produce them by oscillation. So in the early universe, everything is in thermal equilibrium, including standard model neutrinos and standard model leptons. Okay, so processes like these can happen. A E plus and E minus can exchange, convert into two active neutrinos via interactions. If a sterile neutrino, right-handed neutrino exists and have a small mixing with the active neutrinos, in a small fraction of the time, a sterile neutrino can be produced by these diagrams. Okay. So, and through time, a population of the right-handed neutrinos, or sterile neutrinos in this case, can be built out. And dependent on the mixing, which governs the strength of this coupling, you can have a dark matter component. Okay. So this is so-called the Dawson-Virtual scenario, and it's also called non-resonant production scenario. Of course, if there's a non-resonant production, there's also a resonant production. And from neutrino oscillations, we know neutrino oscillation behaves differently when there is a matter effect. So what is the corresponding matter effect in the early universe? one of the possibility is you can have a large lepton asymmetry that's hiding in the neutrino sector because we don't actually know the correct amount of lepton asymmetry in the universe. So this is the effective mixing angle. And what this lepton asymmetry can do to the mixing is, at some point in the early universe, this factor can turn into 0 just because the universe keeps cooling. Okay? And what happens when this factor turns into 0 is you will have an effective maximum mixing. So when this happens, you can have a resonant production of a significant amount of dark matter. Okay? So this is so-called resonant production mechanism. It's interesting in this case is that dark matter can be produced either warm, cool, and cold, depends on the exact parameter. And it's also interesting that in this case, since you need a lepton asymmetry, it can people would like leptogenesis, meaning using lepton asymmetry to produce the observed area asymmetry in the universe, like these kinds of models. Of course, it doesn't have to be produced by mixing. If you have some new particle physics sector, in this case, you can have a new scalar field. Okay? The new scalar field can couple to the sterile neutrinos. Then sterile neutrinos can be produced from decays of these new scalar fields. What's interesting in this scenario is that it does not depend on the mixing parameter. That's very different from the two previous cases. Having a new scalar field is also some people like this scenario because the new scalar field can mix with the Higgs. So this gives you some new ways to probe sterile neutrino dark matter in colliders. Okay. So as I said, if sterile neutrino is a warm dark matter candidate, it can have a non-trivial consequence in the structural formation of the universe. What warm dark matter essentially do is it suppresses the small scale power of the matter power spectrum. Okay. So if you use these power spectrums and you run simulations, this is what you find. So left-hand side here is the cold dark matter simulations. You've all seen these pictures. So many substructures that you can find that later becomes your subhalos and satellite galaxies. If you put in warm dark matter with a sufficient suppression in the small scales, a lot of the structures are washed out. So you have less prominent subhalos. So maybe they can solve the small scale problem. And here, what people study is the effect of warm dark matter in this too big to fail problem. Okay, so from right-hand side to left-hand side is the decreasing temperature of the warm dark matter. So yes, increasing temperature, increasing warmness of the dark matter. So what it brings in is it lowers the velocity curves of the simulated subhalos that better fits observation. Okay. So seems sterile neutrino, if it's a warm dark matter, is very attractive. It may solve some of the small scale problems. So then we need other ways to find this sterile neutrino dark matter. Unfortunately, direct detection is almost hopeless unless there's some new ways to look for neutrino mixing. Okay, because sterile neutrinos don't interact with matter basically at all. We can also look for the effects on astrophysical objects just because they are warm. Okay, and then we can also look at the effects of the mixing indirectly. So this is the main thing that we focus on today. That will help X-ray searches, and also some other effects that, for example, like pulsar cakes, that those are more difficult effects to quantize. Okay, so before talking about the X-rays, let's talk about constraints on sterile neutrino from all the other effects. So, from galaxy dynamics, we know dark matter occupies a finite volume of the phase space. And that constrains dark matter cannot be too light because dark matter occupy, each dark matter occupy a finite number of phase space. And by counting a galaxy phase space and comparing to the prediction upper limit from the primordial phase space, you can set very robust bounds on the dark matter mass. So the current best limit is about 2 to 3 keV. There are other constraints that can be obtained from structure formation. So left-hand side here is studied by counting subhalo counts. So as I said before, if dark matter is very warm, it reduces the amount of subhalos. So you can turn this argument around. If dark matter is too warm, meaning if they're too light, then you will produce too few of subhalos than observation. So turning this argument around, you can again obtain a lower bound on the dark matter mass. And so another place to look for effects of the small scale matter power is from Lyman upper forest. So this is a plot as a function of this scale. So K is one of the scales, so larger K is small scale. And here they test effects of a cold dark matter versus a dark matter candidate that's 2.5 keV, and assuming it's a warm dark matter. And it's a little bit difficult to see, but you can focus in here. So the red dashed line is what you have if the dark matter is warm, and you can see most of the difference between cold dark matter and warm dark matter comes from the smallest scales. So from Lyman alpha forest, then you can also obtain some constraints on sterile neutrino dark matter. Then there's decays of sterile neutrino that you can look for. The primary decay moves sterile neutrinos into free active neutrinos. And again, this unfortunately is hopeless to observe because we have no idea how to observe KV neutrinos at this moment. But fortunately, we have radioactive decay that gives you a neutrino and a photon. Because it's a two-body decay, it gives you a spectral line. And people have said that a spectral line is a smoking gun for dark matter signatures. So another thing is that sterile neutrino is not the only dark matter candidate that can give you a spectral line. There are many different models, and some of the people here comes up with alternatives dark matter models that gives you a line in KV range. So here is an overview of the parameter space for sterile neutrino dark matter. Okay. So the y-axis here is the mixing. Okay. The mixing, basically the degrees of mixing. X-axis here is the mass. From galaxy dynamics and phase space densities, etc., you get a lower bound on the sterile neutrino mass. So anything that's left-hand side of here, it's real. Okay. And for sterile neutrino, you cannot have too small of a mixing if you want to produce enough dark matter abundances through neutrino mixing. Okay. So you also have a lower bound coming from the dark matter abundances. So this line is more model dependent because if sterile neutrino is produced by late decays of some other particles, then it does not depend on mixing. Okay. Lastly, there's X-ray constraints, which goes like this. So anything above this produces too much X-rays, so and then you can put it on. Okay. So what's happening here is then you have a finite empty space. So STEM, yes. Right, so there's many experiments there. I will talk about it. So what's nice thing about sterile neutrino dark matter is if you require it produced by mixing, for example, some of the leptogenesis models, you have finite amount of parameter space. So you have a hope to eventually rule out this class of parameter. So to search the X-ray signals in astrophysical objects, so basically this is what people would do. Right? The amount of X-rays you expect is proportional to basically the decay rate. Okay? And proportional to the amount of the dark matter in the field of view of your experiment. So this is so-called J factor. It's the line of sight integral of the density that's your experiment is looking at. Okay? And then the spectrum of the sterile neutrino is given by delta function because it's a two-body decay. Okay. So now let's look closely again in this plot. And we can divide the mass into two different regions. So low energy, so on left-hand side, and high energy. So just answer your question. So currently the sensitive instruments to the low energy are examine Newton, Chandra, and Suzaku. Okay, so people use those experiments to search for this parameter space. And as you can see, in high energies, actually in much higher energy, in about 50 kV or so, there's an instrument called Integral that's a very sensitive gamma ray telescope, and essentially will sterile neutrino dark matter in those parameter space. But around 20 to 40 kV or so, it's actually beyond the capability of examine Chandra and Suzaku. And if you look at what people have used to look for sterile neutrino in that parameter space, the last instrument that's sensitivity is HEO1 from 1979. Okay? So that's a very, very ancient observation. So there's a small gap here. It's quite annoying that it's difficult to draw. So this is one of the problems that we try to solve, and we put out a paper earlier this year. So what we use is Fermi. So if you guys are familiar with Fermi, you probably only heard of Fermi, which is the box in here that's sensitive to gamma rays in MEV, GeV, TeV. What you may not know is Fermi has a secondary instrument called the gamma ray burst monitors. So these guys. So they're located in all the corners of Fermi, and they're sensitive to all sky that's not blocked by the Earth almost all the time. And as the name suggests, it's sensitive to transients in kV range, like gamma ray burst. So this give us an opportunity to use this experiment to look for sterile neutrino decay. If you think about it, it's actually quite attractive. GBM first, the prerequisite is sensitive to photon energies greater than 10 kV, so there's no competitor. Okay, it has to be all sky, so it looks at a large field of view. Relatively large effective area, those basically the size of those photon multiplier tubes. Decent energy resolution, you need energy resolution to go for a spectral line. So the downside is that it's not very sensitive to a constant point source, which is not a very big problem for us because if we use the nuclear halo is very big in the sky, and so we don't care about the small structures. And maybe the best thing for GBM is that the data is free, so you can just download it and you can play with it. And that's how we started this project. Turns out it's much more complicated than we thought. If you're not looking for transients using GBM, there's a lot of things you need to worry about. First, you need to worry about transients, so you need to cut all the normal GBM signals away. There's also Earth. Earth blocked a large fraction of the data. You need to cut them away. The most annoying effect is actually the magnetic field of the Earth, because most of the counts hits the detector registered as photons, comes from cosmic rays hitting the detector, and that significantly correlates with the Earth's magnetic field. And the most annoying part of the Earth's magnetic field is a region called the South Atlantic anomaly. In fact, it's so the magnetic activity in the South Atlantic anomaly is so high that Fermi stopped running when it enters there. Okay. So after taking all these effects into account, we obtain a sky map. And you see something in the center of the sky map. Yes, because we found the Milky Way in 10 kV. So the Milky Way exists in 10 kV. It may not seem significant to you, but to my knowledge, this is only sky map in 10 kV. So if you think of a use to this, though crappy, but unique sky map, we should thank you.
What's that hole?
This hole?
Yeah.
We don't have observation tools that sky picks. It's a hole. It's near the orbital hole. Okay. So having a map And then we can pick out the regions where you expect there's more dark matter, so you're more sensitive to dark matter decay. Then we can look at the spectrum. Okay, so this is the spectrum. One is towards the galactic center, one is towards the anti-galactic center, and the difference there is due to the galaxy astrophysical component itself. Having the spectrum, you can ask, what's the maximum amount of dark matter signals you can tolerate? And from that, you can get a constraint. So this is the GBM constraint that we obtained. The blue hashed region. And the green region is the old constraints obtained from Hill 1. So we successfully improved the limit of our one order perspective in this energy range. Unfortunately, we cannot quite close all of the parameter space in this region. Okay, so there's some gap here. So then, what can we do next to fully probe this? Yes.
That angles, which example is that?
This is the active and sterile mixing.
With also.
So this uses two flavor percentage. Yes. So if you put in 3 plus 1, then it will be the sum of both. So what's next in this particular energy range? Of course, we can improve GBM observations. This is the only first attempt in using GBM to do dark matter physics. And our data is statistically limited. We have too many photon counts. It's limited by systematics. So the data is not statistically limited. So if you can find a way to improve the data analysis, you may get very strong constraints. Or you can use a new instrument that's actually launched in 2003, USTAR, that's actually also sensitive to this energy range. Okay, so in fact, people have already used USTAR to look for dark matter already. But currently, the limit is not as strong as GBM. But we'll see what this thing can do. Okay. Now let's go back to this plot. Let's at this moment forget about this and look at the low energy range. And I told you that XMM, Chanja, and Susaku is sensitive to this energy range. So for many years, people have used this instrument to look for sterile neutrinos. And there has been claims that's been made. Around 2010, 2012, people claimed they find 2.5 keV line, so that corresponds to a 5 keV sterile neutrino candidate. And the same group of people later decided, it's not actually a real dark matter. Okay, and also people have found claim they find excess of 8.5 keV lines, so that corresponds to 17 keV sterile neutrino. Not a lot of people follow up on this, so I guess people realize it's quite difficult to find a dark matter in this range.
Is that for a long time ago, or is that from?
It's 2000.
That's recent. Okay.
2009, 10-ish.
There was 17 EV neutrino. Okay.
Yeah.
Right, sorry.
Yes. Okay. So people have tried and people have failed. And then, of course, there's the latest episode is people found a 3.5 keV line. That's consistent with a 7 keV sterile neutrino. But this time people actually seems to be doing a very careful job. And what they have done, the first group is they stack a bunch of galaxy clusters. So because the galaxy clusters, each of them have a different redshift. Okay? So to stack them, you need to de-redshift off them to the rest frame. And what this can do is it can negate much of the detector systematics, because detector systematics does not depend on the redshift of the objects. Okay? So this supposedly should increase your signal to noise. And in fact, they find 4 to 5 sigma of the excess and 3.5 keV. And a week later, another group reports they find a line in a similar energy range in one individual cluster and also in the NW1. Okay. So this, of course, for this time, a lot of people have followed up, and a lot of debate has centered on this particular sterile neutrino. So just to summarize, so people have used many, basically the same instruments and also Suzaku to check for different systems. So they have checked for galactic center with 2 instruments. Some find a signal, and some claim that the signal, they find a line, but the line could be consistent with with atomic lines if you do a different model. Okay, and then people stack galaxies, and then people look at dwarfs, and then people look at various different places. There's still a debate going on, and of course Louis has to also work on this. Louis found a line in one cluster, and Gideon found a line in several other clusters.
Is that my fault?
Yes. Okay. People are still debating, but seems so not detecting the line is not the only handle, right, to decide whether it's dark matter. So people also look at does the morphology looks like a dark matter density profiles, and people have doubts on this. Okay, and because the modeling of the background depends a lot on the atomic abundances, and then people try different ways to model it, and then determine how robust the signal really is. And then most of the studies claim that the signal is not does not 100% looks like a dark matter. Okay, but the latest development is from the first group that they found sterile neutrino dark matter. Now they look at individual clusters, okay, and instead of stacking them. The recent development is that they claim in many of the clusters they detected the line individually. Okay. Now if you plot the detected flux versus the projected dark matter flux, right? Dark matter is supposed to have one single decay lifetime, so they should correlate like this. And they claim that okay, you may have a correlation there. So this seems very interesting, but it also means that the debate will continue. So earlier I said that a spectral line is called a smoking gun for dark matter signals. Perhaps not in this case. So is there a solution? Currently, personally I'm not very optimistic on that because both Chandra, Alexander Newton, and Suzaku, they're 10 years old. So there's not much new data you can gain from them. But you can look forward to new instruments. There's 2 particularly interesting instruments. One is the Astro Age. It's a narrow field of view, so you only look at a very small patch of the sky, satellite emission. What's special about Astro Age is one of the instruments on Astro Age has approximately 10 to the minus 3 energy resolution. It's like 30 times better than the current instruments. Another instrument that is called Micro X. It's actually a rocket. It has a very wide field of view, so you look at a large patch of the sky. It also has a very good energy resolution. But the only downside is that these instruments only look for the patch of the sky for a very small amount of time, because the rocket fly up, and then after about 100 seconds, it fly down. So these 2 instruments both have very good energy resolution. So a good energy resolution can help is to avoid being confused with atomic lines. So what's shown here is the line spectrum of several atomic lines that you may confuse with this 3.5 keV if it's really dark matter. So with the current instrument's energy resolution, you get very broad spectral distributions. But with energy resolution of Astro Age, you can actually resolve them. So for example, in the wall down on the left, you can actually see it actually consists of 3 different atomic lines. So the hope is that using a more an instrument with more refined energy resolution, you can separate atomic lines or maybe unknown dark matter. Okay. So of course, you still may have the problem is that dark matter line can be lying somewhere here. You may still be confused. And much of these atomic line emission comes from how you model the abundance. That's also very large uncertainty. Okay. So another idea that people come up with a good energy resolution is maybe now dark matter does not look like a delta function to your instrument. So with 10 to the -3 energy resolution, dark matter turns out can actually sensitive to the dark matter velocities in the cluster. So this is coming from a simulation, and all of these are atomic lines. And here they put in a dark matter line in a cluster with 1,000 kilometers per second dispersion. And what they claim is, with astro age, you can actually resolve the non-zero width of this line. And if it looks like that, it's more likely to be dark matter than atomic lines. But of course, this again requires you looking at a cluster, which itself is bright in X-ray. And it depends on how well do you really determine velocities of the competing atomic models. Okay. So this actually got us thinking about a similar idea, but instead of using line widths, we think maybe we can use a different velocity effect. It's called line shifts. So people have looked at line shifts in the galaxy for a very long time, both in looking for molecular gas and also gamma rays from the aluminum. What people have found is that if you take a galaxy, if you look at positive longitude, so that's the left-hand side, you will see a positive velocity, meaning these gases are running away from you. Okay? If you look at the negative longitude, you find that the gas is running towards you. So you have a negative velocity, and negative velocity means a fusion. So, and if you look at these, the scale is about hundreds of kilometers per second. That means an instrument with 10 to the -3 resolution, delta E over E, will be sensitive to these shifts. Okay, so maybe this can be have some interesting application for dark matter. So, but let's try to understand why you get this asymmetry first. So if you look at the gas of the Milky Way, we are living in a co-rotating disk. Right? So the sun is here, and every baryon is co-rotating in a disk. So the sun is moving in this direction. And if you look at a point towards the positive longitude, for example, a point gas in here, because the co-rotation, what you will find is that the gas is running away from you. So this is correct as long as that point is within the distance of the radial distance of the sun. Okay. So then correspondingly, if you look at a point in the negative longitude, you will see the gas is running towards you, so you see a blue shift. Okay. So this is what happens for a gas. For dark matter, the picture is actually different because dark matter does not co-rotate with the baryons. Dark matter has a non-zero dispersion, but essentially the dark matter halo is stationary. It has a net zero velocity. Okay. So, but the sun is moving. So if you look at a point in the plus longitude, what you will find is that the dark matter is running towards you just because of your own motion. Okay. So you will see a blue shift, Doppler blue shift towards the positive longitude. And correspondingly, you will see a red shift in the negative longitude. So what this find is very interesting is that in the same direction, if an atomic emission emits a line, it will give you a red shift. But if dark matter emits a line, it gives you blue shift. This gives you a nice handle to distinguish dark matter emissions from atomic emissions. Okay, so to model this, turns out we need to model both line shifts and line waves. And so we have done this in the earlier paper, earlier this year. Okay, So normally, when you calculate the intensity, you assume a delta function approximation for spectrum. Okay, but once velocity effects become important, these two factors cannot separate. So both the dark matter density distribution and the spectrum cannot separate. Now you need to do the line of psi e to go together as a function of energy that takes into account both dispersion and shifts. Okay, so now I have actual calculation instead of the cartoon. If you look at a direction in the plus longitude, okay, so you will have a dark matter and dark matter bump looks like this, and this is compute with the H2H energy resolution. So if you see a line with the same strength, but if it follows the distribution of a baryon, you will have redshift. Okay? So if you have good enough energy resolution to separate these two hypotheses, now you have an extra handle in separating dark matter versus atomic. Okay? So by the way, if you look at the effect here, it's about 0.1%. So you do need 10 to the minus 3 energy resolutions to do that. and if you wonder what it will look like if you use current instruments like XMM, so the XMM bump looks like this, and then these two is actually these two. Sorry, this peak is these two lines string together. So you probably won't see anything. Okay. So then now you can look at the line shift you expect as a function of the galactic longitude, as a function of where you look. Okay. So shows you for baryons, depends on the baryon models, different baryon models. You all expect a positive velocity or a redshift towards the plus longitude direction, and opposite the negative longitude direction. And this is what you expect for dark matter. Okay. And we checked with H2H, if you look at somewhere like 20 degree longitude and slightly off the plane to reduce the continuum background, you will have enough photon counts to significantly detect the 3.5 kV line, and you also have enough photon counts to get the line shift separation. So we call this the velocity spectroscopy idea. Okay, so if the smoking gun is not good enough, maybe this velocity spectroscopy can give you an extra handle in designing, in determining whether it's dark matter or not. Okay. So, and if you think about it, this idea is actually general. It does not only work on sterile neutrino. Any dark matter that gives you a line can work. Question?
Well, cameras will probably have that sensitivity, but for X-rays, so because this situation will also be anywhere in any galaxy, right? So if it's a gas, you get a smear because the velocity goes ways.
Yes.
And if it's dark matter, they stay there. We don't have this thermal smearing. And then, so can we resolve that in some X-rays in some other galaxies?
So the only nearby galaxies to us that can possibly do this is M31. So we look at M31. So M31, what happens is you get a net shift for the dark matter, and if you can resolve the baryon disk, you will have a non-zero velocity structure. So that's
Magellanic Cloud.
we didn't check Magellanic Cloud. Does Magellanic Cloud rotate?
Yes.
Okay, so that might be interesting.
Yes. Yes.
Rotate in our line of sight direction.
Oh, that's what question.
Yes, we need a line of sight direction. But anyway, it's general to dark matter, and if fortunately dark matter do gives you a line, for example, if dark matter really is the 3.5 kV line, this actually allows you to do some dark astronomy, because at this point, nobody have actually measured the velocity distribution of dark matter. But if dark matter gives you a line, and you can resolve the wave, it actually tells you the velocity of dark matter for the first time. Okay, and actually the possibility does not stop here. If you think about it, the decay lifetime of a dark matter is a cosmological constant. So it's a constant in cosmology. in cosmology sense. So it can actually allow you to do some cosmology. So this would be very interesting if dark matter really is the free conductivity. Okay. So SOH is not the only instrument in the pipeline that can possibly do this. So the Europeans are thinking of a new instrument called Athena. That's actually a significant upgrade to SOH, but it will, it's a little bit later in terms of the lifetime. And you talk about gamma rays, actually there's a proposal for a gamma ray detector and also lepton detectors in the Chinese space station, once it exists, that it will have a similar, it will possibly have a similar energy resolution for these high energy particles. Okay, so maybe this idea of velocity spectroscopy can extend to other studies. We'll see.
Another thing is if they cycle around the assembly, there's also thermal velocity distribution.
Yes, so that contributes to dispersion.
So that's one.
No, so that's what determines. That's why these two have a different width. That is the coming from the thermal phase.
So the dark matter is like all thermal, if you will. I think in what you're saying.
So the peak is the peak and states.
Yes. So what you need is just number of photons to determine the centroid of the line. Yes. Okay. So hopefully, velocity spectroscopy will be useful once SOH is launched. Okay. So just to conclude, X-ray observations are powerful for sterile neutrino dark matter. Okay. So with GBM, we tested sterile neutrinos about 20 keV mass. Maybe with new star, we can fully close that parameter space. Okay. So the original 3.5 keV line is still being debated. With SOH and maybe with the velocity shift, you can definitively test whether it's dark matter or atomic lines. And with new instruments, maybe the whole parameters will be closed soon. Then what it means does not mean the end of sterile neutrino dark matter. It means we need new production mechanisms other than oxidation.
Any questions? Any further questions? So you probably just did the simplest case where the dark matter is isotropic.
Yes.
To calculate its dispersion, have you estimated how your curve might change if you made, say, the dark matter more anisotropic in some way?
No, we may not do it.
Okay, so he's around today and tomorrow. So, good, the 4th. Okay, thanks again.
Thank you.